Good morning, everybody, and thank you for joining this webinar. My role within this webinar is to cast some light, hopefully, on the material perspective. I'm a material scientist, and I was trying to shift to the next slide. Oh, no, yeah, now it works. Yeah, I was asked to give some more information on the possible defects we may happen to see in some of the reference material of our projects. Actually, our project, as Jörg already told us, considers laser beam welding of stainless steels, and the related topics will be dealt with in other presentation. And the second point was about laser powder bed fusion of nickel-based superalloys. I will focus mainly on this point here. Especially, we have been working on some high-strength nickel-based superalloy, Inconel 713LC and CM247LC alloys, and they are actually quite critical in processing. First of all, I would just wanted to give you a few preliminary information for those of you that are not familiar with nickel-based superalloys. This is a typical microstructure of a cast nickel-based alloy. It is made of a matrix made of nickel solid solution. It's called the gamma phase. Nickel is actually alloyed with cobalt, chromium, molybdenum, and some other stuff in most of the nickel-based alloys. And then we have the strengthening effect, which is promoted by the presence of a quite large amount of gamma prime precipitates that are at high magnification. They can be seen as some kind of cubes, like those over there here. They are based on the nickel-3 aluminum crystal structure. Actually, aluminum is replaced partially by titanium, tantalum, and so on. Sometimes you can also add niobium, and then we can talk about gamma double prime. And finally, last but not least, also we have to deal with the dispersion of carbides at the grain boundary. Usually there are carbides rich in titanium, tantalum, hafnium, and so on. They might be carbides or borides, in case there is boron in the chemistry of the alloy. I can tell you that the most diluted nickel-based alloys are really weldable, really processable by laser powder bed fusion. However, when we move to higher strength alloy, which is our case, then we move to a condition where the alloys are not so well processable anymore. We can use such kind of diagrams, such kind of maps. They call them weldability maps because they come from welding science, that show that when we move in terms of aluminum content and titanium content, when we move in the upper right corner of this diagram, we move in a critical region. And actually, with our alloy, we are in a critical region. So we expect to have some troubles. And then, when focusing on laser powder bed fusion, just a few words to understand what we are dealing with. Laser powder bed fusion is a process which allows us to create 3D objects by the repeated deposition or let's say remelting of layer after layer by melting a powder bed by a laser. So the laser selectively melts a shape on this plane here, and then repeating track by track and layer by layer this process, we can build up a 3D object. So the object is built up track by track along a given plane, and layer by layer along a given direction of building direction. It's a matter of melting powder by the laser absorption. Here in the following slides, I'm gonna show you some experimental results must tell you that these results or this experimental activity was carried out not to solve the problem, but to understand in a deeper way, to acquire more knowledge about the defects we have to fight against. So we used a standard commercial powder of, for instance, in this case, of the CM247LC alloy, which is a very nice spherical powder. And by a standard machine, without any beam splitting and any special option, we made some prints trying to optimize and trying to get the best result as possible from the standard laser powder bed fusion process. So this is the powder we are dealing with. It's made up of nickel base alloy with quite significant amount of chromium, cobalt, tungsten as well, and together with titanium, aluminum, and hafnium and titanium. And these are the cubes we printed to check the microstructure and the presence of possible defects. That's the microstructure we can get even after parameter optimization. When you produce a section of the material, you can recognize in the microstructure the tracks of the traces of the different melt pools. They are partially overlapped. When you go higher with the magnification, you can see the columnar elongated grains that are growing almost in a vertical direction, which corresponds to the build direction. And if you increase even more the magnification, the level here is 300 nanometer. If we go to very high magnification, then we can distinguish inside the single grains some small cells, some micrometric cells that are decorated with carbides. Also, you might have seen them, I might have noticed them, we are dealing with some cracks, even after parameter optimization with a standard laser powder bed fusion process. We cannot avoid having them. They run across the melt pool tracks, usually crossing several melt pools. If we focus more on cracks, we can see that they span from a size from about 10 micrometers up to more than 300 micrometers. And by looking at EBSD maps, EBSD stands for electron backscatter diffraction, we can get some information about the grain boundary structure. Especially this colored map shows the different crystal orientation. Different colors mean different crystal orientation. We can see that crack grows along the grain boundary. Different grains, they do have different crystal orientation. The crack grows especially where the orientation is very high. The mis-orientation, is very high. The color contrast is very sharp. When we move into a single grain or along grains that have small mis-orientation, then the crack stops. So the information you can get from this kind of result is that the crack, they grow in a intergranular mode, trying to run along the grain that are highly mis-oriented. We call them high-angle grain boundaries. Then also some other useful information we can get from X-ray EDS maps that show us the distribution of the elements close to cracks. So this is a high magnification view of a crack, and these are maps of the different elements. So around the crack there is a matrix made of nickel with a solution of chromium and cobalt, but close to the faces of the crack there are segregation of carbides reaching hafnium and titanium. You can see the bright spot over there. And also within the crack faces you can see enrichment of aluminum and oxygen. All those segregation are considered quite important because they make the solidification range quite wider, let's say, and this helps in promoting a crack. Based on this information and also based on the literature, we can distinguish in nickel-based superalloys among 4 different sources of defects. The most important for us are the first two. So we can talk about solidification cracking formed in the weld bead or in the material under solidification during laser powder bed fusion processing. When we have a mushy zone, namely a semi-solid zone with a large fraction of solids, that is experiencing quite high tensile stresses because of the shrinkage, of thermal shrinkage. And the small amount of liquid at the grain boundary easily develop cracks. A second, which is quite similar source of defect is grain boundary liquation cracking. The name comes from the welding science, and this especially occurs in heat effective zone. It forms as a result of the local dissolution of the low melting point phases, as we saw before, and this liquid film that forms failed again under the thermal stresses. And then we can also have strainage and cracking and ductility deep cracking, but they are sort of solid phase damage and phenomenon, which is not important for us at the moment. Now, what do we do finally against these defects? There are two basic routes, I would say. One is modifying the chemistry of the alloy. It's a very challenging and time-consuming strategy, which requires a lot of certification, a lot of qualification and certification for the new material. This is not our route. Our strategy is more toward fine-tuning the processing condition in order to mitigate the cracking phenomenon. And this is the objective of the Custodian project. In general terms, you can see on the right side of the slide that we saw different damage phenomena in the alloy. Actually, for our nickel-based alloy, we span out quite a wide range of temperature on which we may have this damaging phenomena. Especially, we want to focus on the solidification-associated phenomena, which occur in the very top side of the temperature range. So we know that fast cooling is a quite critical condition for the crack development. Fast cooling rate is during solidification is, I would say, unavoidable with laser processing, but could be mitigated by preheating, for instance. And this allows slowing down the cooling rate and mitigate the cracking. Also, reduced cooling rate during the very final fast stage of the solidification could help in mitigating the phenomenon of liquation cracking. And then, if we want to, slowing down here, and then if in the ideal world, I would say, if we want to optimize things, we can also speed out the cooling rate after that in the solid stage and fix or hold the material at the proper aging condition. But it's ideal, of course. What we have to consider in a real laser powder bed fusion process is that the thermal cycles, let's say that the material is not subjected to a single thermal cycle, but you have to talk about several thermal cycles that are induced because of the result of the combination of the several heating and cooling cycles given by each single laser scan on a single layer and by the repeated effect of the overlapping layers. Here are some plots about the multipass effect on the thermal cycles of a real process on our reference material. So this is the actual thermal cycle a material is feeling under this kind of processing condition. So it's not really easy to predict and to imagine a simple thermal cycle to be given to the material. For this reason, we need accurate processing of simulation in order to select a modified laser process cycle and, of course, the most appropriate beam splitting modes in order to produce beneficial pre- and post-heating treatment. So this was my introductory talk about the, the condition we have to deal with about considering the material perspective.